Hello, welcome again. In this video, we're going to look at Faraday's and Lenz's law, and we're going to begin to formulate how a change in magnetic field creates an electric field and how a change in electric field creates a magnetic field. So here we go. Now, we've already seen actually that a current can produce a magnetic field. Okay, we've seen that many times. Michael Faraday wondered if a magnetic field then can produce a current. You see that? That's kind of reverse thinking. This type of thinking happens in physics quite a bit. And Michael Faraday found that a change in magnetic flux induces a voltage, which creates a current then. So again, a change in magnetic flux is what induces a voltage, and then that voltage can create a current. So the voltage in this situation, this induced voltage, is usually called electromotive force, or EMF. So I'm just going to write that down, electromotive force. And you can just think of this thing as a voltage. Really, it's no different than if you had a battery, let's say, or an AC source maybe. You can just think of it as a voltage. It's given a fancy name, electromotive force, and it's just it's just in this context of, hey, a changing magnetic field is what's causing this voltage. So in that case, we're going to call it electromotive force, or EMF. All right, so now I want to draw your attention to this first figure that I have over here in the top left. So in this figure, a rectangular loop is inside a magnetic field B, such that B is coming out of the page and becomes stronger as you move to the left. So you can see that because the magnetic field lines are getting more dense to the left. So now if nothing changes, if that picture is just there and it's there for all time, then there is no change in, if nothing's changing, then the flux of B through S, loop S, then that flux is not changing, and then there is no current in the loop. Remember, Faraday said that the EMF is generated from a change in flux. So if B does not change and if S does not change, then there is no change in flux and there is no voltage that's induced, and then there's no current in that conductive loop. Now, in this example, there are, I count 4 ways to change the flux of B through S. So let's talk about the ways of changing that flux. So one is that we can increase or decrease B. That is, make B time varying, right? So if maybe we had some sort of control of the magnetic field, and so we have a dial, and so we can crank it up or we can decrease it, and we can vary it with time. And if we vary it with time, that's a change in magnetic flux then through loop S, and that will, believe it or not, induce a voltage in that loop, which will produce a current. This is just what Faraday saw experimentally. Okay, the second way we can change the flux is we can move S to the left or to the right. So certainly that if I move it to the left, then since the magnetic field increases, then the flux will increase as well. So there will be a change in flux in that case. So remember, change in flux. So we're talking about the derivative of flux versus time. So if we move the loop to the left, then the d psi dt then will be positive. There will be a positive change in flux. And then if we were to move it back to the right, there would be a negative change in flux because the field or the flux is decreasing as we go to the right. So either way, we have a change in flux, and so we would have an induced voltage in that loop, which produces current. Now, if we move the loop up or down from where it is, notice that the field is independent in that direction. And so if we move the loop up or down, we're not really changing the flux then. And so we would not have, in this example, an induced voltage. Number three, a third way we could change the flux is we could actually rotate S around an axis. Maybe around an axis that goes up and down, like this. So, imagine the loop coming out at you and then going back into the page and rotating around that axis. So certainly then, once the loop is fully out of the page or out of the screen, then it's parallel to the magnetic field and there is no flux at that point. And so the flux is zero, and then when it goes back into the page, the flux is, there's flux there, and then, so this is all to say that it changes the flux as S rotates around that axis, and again, a change in flux creates an induced voltage. And a fourth way I see is that we could just change the loop. We could change the dimensions. Although this is less practical, it turns out. We could change the dimensions of S. So maybe we have some sort of loop that is able to be adjusted on the fly. So maybe its height and its width we can play with somehow, right? And so if we can change the dimensions of the loop, then again, there will be, if we say we decrease one of the dimensions, then the surface area decreases, and then the flux, which is related to the area, would decrease, and so there would be a change in flux that way. All right, so I want to focus on actually point 2 here, where we move S to the left or the right. So consider that case. If we move S to the left, the magnetic flux would increase since B increases, and a voltage is induced and a current flows in the loop. The question is, what is the direction of the current? Or what is the direction of the, what is the polarity of the induced voltage? So that's what I want to answer right now. So it turns out, and this is, we'll have more to say about this in a little bit, but it turns out the direction of the current is such that it counters the change with its own magnetic flux. Remember, a current in a loop creates a magnetic flux, or a magnetic field. So in this case, if we move the loop to the left, there's an increase in magnetic flux out of the page. So the induced current will be in a direction this way, clockwise, such that the magnetic field caused by I will counter that change. So it will decrease the flux. If you remember from the right-hand rule, that the direction of the magnetic field due to that current will be into the page in the loop. So it has to be that way. It has to counter that change. And then if we move the loop back to the right, then this will make a current that is counterclockwise in the loop for the exact opposite reason. So mathematically then, what we've said here, if we sum all this up with some mathematics, is that the induced voltage, or VEMF, is negative the change in flux, magnetic flux, with time, like that. And the negative sign comes about because of this idea that the induced voltage and the induced current produces a magnetic field that counters the increase, or the d psi dt. And this is what is known as Faraday's law. And Faraday's law has many different forms, and we'll get to those forms actually right now. So remember that flux is related to the magnetic field B and the area. So we can write the induced voltage like this. The flux is the integral of B dot ds. And remember that the voltage is the path integral of the electric field. So I can write the induced voltage as this path integral of E dot dl, like this. Perfect. Now, it's it's usually the case that the area of the loop does not change, that the dimensions, it's not really practical to be able to change the dimensions of the loop. So in that case, and in only that case, we're able to bring the derivative in then as a partial derivative just operating on B instead of the surface area. So this would be negative the integral over S of, and it's a partial derivative now because it's operating on B because we took it inside the integral, B dot ds like this. Okay, and now with Stoke's theorem, remember Stoke's theorem relates a closed line integral with the curl and a surface integral. So now the left over here with Stoke's theorem would become a surface integral, the surface area of this closed loop of the curl of E dotted with ds, and then that equals, and then if I look at the right, would be equal to negative integral over S of the partial derivative on B dotted with ds, like that. And then since I have the same integral over this surface area, then the integrands must be the same, and we see that the curl of E must be the time derivative, negative time derivative of B. Right, and so this is the point form or the differential form of Faraday's law, and this is one of the Maxwell equations. Right. Now Faraday's law applies to any loop and any magnetic field, not simply this example on the top left that I've introduced. So this is true in general. And as we said, the induced current must oppose the change in flux. That's the reason for this negative sign. So now it turns out that Faraday actually didn't know about this negative sign. He didn't quite get there. So the negative sign was actually introduced by Lenz. And so Lenz's law is this idea that it counters the induced magnetic field, or the induced current counters the change in electric flux, or excuse me, counters the change in magnetic flux. So I want to take a closer look at that direction of the magnetic field, a closer look at Lenz's law, this opposition idea. So I'll turn your attention to this second figure I have down here at the bottom left. So let's take a look at a different example where I have a magnetic field constant, or constant in space, that is just pointing up, maybe the z-axis, and then I have this rectangular loop in green that's maybe in the xy plane, like that. And let's say the loop remains constant, static, and the magnetic field increases. Okay, so let's say the magnetic field increases. And so we just said that that increase in flux then is going to produce a voltage, which produces a current. And so I've got two figures here, one where the current is going, clockwise around the loop, and one where the current is going counterclockwise. And our job is to figure out which is the correct way, right? The only one of these is correct. So again, B is increasing in both of these pictures. So I've got that in orange here, B increasing, B increasing. Now, in the top figure, if the current is going clockwise, and you use your right hand for the right hand rule, and I've kind of got a really bad drawing right here of this, but you point your thumb, remember, in the direction of current. So maybe let's take a look at this side, where the current is coming kind of out of the page. And if you point your thumb of your right hand in that direction, like the illustration, and you curl your fingers, then inside the loop, your fingers should be going down, right? And so that means this current I in red produces a magnetic field that goes down. And then if we go over to the right, you'll see the same thing happening, where now you point your thumb into the page, and when you curl your fingers, you're curling them this way, and still inside the loop, your fingers curl downward. So this current in the top figure, this induced current makes a magnetic field that points down. So remember, it has to counter. So we've got B, and then B increases, And so now this current would be countering that increase in flux by making a flux that points downward or decreasing the net flux. And so, this is the correct case. And let's look at now the second case down here and see why that's not correct. So if I look, let's concentrate on this arrow here at the right. So if I point my thumb of my right hand in that direction and I curl my fingers, you'll see, like the illustration here, you'll see your fingers are curling this way in the direction of the positive change. So in this case, that would seem to add to the change, or definitely not opposing it. In fact, if we looked at this arrow here, we could make the same argument, point your thumb in that direction, curl your fingers, and your fingers come down like this, and then inside the loop your fingers go up, and again, and so we end up with the same conclusion that this current, this counterclockwise current, is adding to that change in electric flux. So this bottom change, this would be like a positive feedback thing, and this would continue without bound, just go towards infinity. You need some sort of countering, and this is absurd. You can't have this change in magnetic field that keeps continuously adding to the change in flux. So this would be the wrong situation here, and it's this situation which is correct. And again, that's known as Lenz's law, the fact that that induced current opposes the change in magnetic flux. So that was a lot, and let's look at a few examples now that I have coming up for you. Thank you.